Hello, everyone. I'm Brad Scheller, and in this video, I'm going to talk about one of the biggest shifts in business that has had a tremendous impact on company valuations, and as a result, is now becoming a driving force in business. But let me start with a question. How long do you think it takes a car company like Toyota or BMW, to design and build a brand new car from scratch? Most big automobile manufacturers take 5 to 7 years. 7 years. That's longer than it takes to get a college degree. Now, what if I told you there's a method used at Tesla and SpaceX right now that can make 27 major hardware changes in a single week? Not 7 years, 1 week. That's what this presentation is about. It's called Extreme Manufacturing, or XM for short. And by the time we're done today, you're going to see why the companies using XM are worth hundreds of billions of dollars more than the ones stuck in the traditional way of manufacturing. So let's go. So let's start by looking at this chart. It's comparing three ways of making things and what each approach is worth on the stock market today. Traditional automakers, companies like Volkswagen, BMW, and Daimler, they take 5 to 7 years to complete one full design cycle. Their combined market cap, around $181 billion. Toyota's approach, called Lean or Toyota Production System, TPS, cut that down to 2.5 to 4 years. And it worked really well. Toyota by itself is worth around $210 billion. But now let's take a look at Tesla. Tesla isn't measuring in years. They're measuring in hardware changes per week, 27 changes per week. And their market cap blew past others, $800 billion. Here's the key idea from Elon Musk. He has said that the pace of innovation is all that matters in the long run. He's not saying quality doesn't matter or safety doesn't matter. He's saying that the company that can try more things, learn faster, and improve faster, that company value will be outpace everyone else. That company wins every time. Traditional companies optimize so nothing goes wrong. XM companies optimize to learn as fast as possible. That one shift in mindset is worth hundreds of billions of dollars. On this slide, we see a comparison table of three ways companies build physical products. Think of it like comparing different operating systems on a computer. First column, waterfall. This is the old school approach. You plan everything out in advance, you hand off between departments, and pray nothing changes. The core goal, predictability. The problem, the world changes whether you want it to or not. The second column, lean or the Toyota production system. Toyota improved on Waterfall massively. They cut waste, they improved quality, but the process is still basically linear. One piece flows through the system at a time. Think of it like a single lane road. It's efficient until someone slows down. The third column, extreme manufacturing. XM blows the old model up entirely. Instead of one lane, it's a highway with multiple lanes running at the same time. Teams work in parallel. They're organized around independent modules, not departments. And changes happen multiple times a day, not every few years. The analogy here is really helpful. Lean is like a single-threaded computer processor. It's fast, but one bottleneck stops everything. XM is like a multi-core processor. If one core slows down, the others keep moving. When you design a product from the start to work this way, you can move at completely different speeds. Now, here's one of the most powerful ideas in this whole presentation, and it sounds almost too simple. The way you organize your team determines what your product looks like. There's a famous idea called Conway's Law. It's from 1960s. It says organizations design systems that mirror their own communication structure. In other words, if your engineering team is siloed in separate departments, your product is going to be tangled and hard to change. Look at the left side of this diagram. That's what a legacy rocket or a legacy product looks like when built by a siloed organization. Everything is connected to everything else. Change one thing and you risk breaking 10 other things. It's a mess. Now, Joe Justice, and that is his real name, the creator of extreme manufacturing, extended this idea. He calls it Justice's Law. If you want a modular product, you need a modular organization. Look at the right side. Instead of one big chain where mechanical engineers hand off to software, which hands off to testing, you have small teams, each owning a module. Every team has mechanical, software, and testing together. They can work completely independently. The result, the product snaps together like Legos, and you can update one module without touching the others. This is how SpaceX built the Falcon Heavy, and it's a complete rethink of how companies should be structured. Now I'm going to talk about one of the coolest technical ideas in XM, and it comes directly from software, of course. In software, there's a concept called object-oriented programming. The big idea is that different parts of a program talk to each other through defined rules called interfaces. As long as those rules stay the same, each piece can be redesigned independently. Now, XM applies the same idea to physical hardware. Look at this car diagram. The green panels represent the interfaces, the defined connection between points, between modules. Things, for example, like a bolt pattern. What size and grade bolts connect this part? Or data and power. What voltage and connector type? Or fluid dynamics. The maximum temperature at the connection point. And here's the key insight. As long as those specifications stay locked, as long as the contract between modules is stable, the team responsible for the module behind that interface can redesign it completely. New material, new shape, new manufacturing processes. Nobody else has to even know. And the data point on this slide says it all. The return on investment for spending extra time to build a really solid interface contract pays off within 3 sprints. Why? Because everything after that runs in parallel. This is why Tesla can push software updates that change hardware behavior. The interfaces are defined. Everything else is flexible. In software engineering, there are reusable solutions called design patterns. When you have a common problem, you reach for the right pattern. XM brings 3 of those patterns into the physical world. Pattern number 1, the adapter pattern. Imagine you have a new, better suspension component, but it doesn't quite fit the existing chassis. Instead of redesigning the whole car, you build a small adapter plate, a hot swappable interface that makes the new part fit. You keep the old architecture and you bolt in the improvement. Fast and low risk. Pattern number 2, the wrapper pattern. Sometimes you buy a part from a supplier, but you need to protect yourself if that supplier changes their design. So you wrap it. You build a custom housing around it that matches your interface's specs. So if the supplier changes their part tomorrow, all you have to do is redo the wrapper, not the whole car. Pattern number 3, the decorator pattern. This is the most futuristic one. You build an abstract factory. Think of it like a base model coming off the line. And then at every end, robots customize it. Different paint job, performance tuning, trim options, all done dynamically at the end of the line without slowing anything down. The big idea across all 3, stop engineering from scratch every time. Borrow, adapt, and wrap what already exists. And that's how you move fast in hardware. Now, there are a lot of concepts borrowed from object-oriented programming, and here's one that I particularly think is great. It sounds backward at first, but it's brilliant. In software, test-driven development means you write the test before you write the code. You define what done looks like before you start building. Then you write the minimum code to pass that test. Then you clean it up. XM does the exact same thing with physical parts. Step 1, red is fail. Before you design the part, you build the robotic test fixture. You define exactly what the part has to do to pass. Maximum stress, minimum weight, specific bolt pattern. You run the test against your first prototype. It fails. That's fine. That's the point. Now you know exactly what you're solving for. Step 2, green. This is a pass. Now you build the cheapest, fastest physical thing that passes the test. It doesn't have to be pretty. It doesn't have to be light. It just has to pass the test. duct tape and zip ties if necessary. You just need to prove it's possible. Step 3, refactor, optimize. Now you know how it works, and you know it works, and you redesign it for real, for manufacturing, for cost and weight. And when you rerun the test, it passes again. This approach eliminates wasted design cycles. You never over-engineer before you know what the test actually requires. It's a brilliant concept. So let's talk about what this means if you're designing actual physical products and not software. So if you were going to design the perfect physical workspace for fast hardware development, what would it look like? Well, XM has a specific answer. There are 7 practices that define how the shop floor is set up. Number 1 is always open. The workspace is available 24 hours a day, 365 days a year. There's no waiting for someone to unlock the building. Empowerment over permission. If you have an idea at 2 a.m., go build it. Number 2, snack shelf. Sustained energy. Sounds silly until you realize that hungry engineers who have to leave the building to eat lose momentum. Keep the team fueled and in flow. Number 3, safety shelf. Visible personal protective equipment, or PPE, emergency procedures, all in one place, always accessible. Number 4, visible inventory. Everything you need should be visible from one standing spot. No hunting through cabinets. No, who has the M8 bolts? If you can't see it, it slows you down. Number 5, Kanban of tests. A board that shows which tests are passing and which are failing, and what's between the team and the definition of done. Everyone knows the score at all times. Number 6, cleaning shelf. This is 5S discipline for speed. The floor should be clean enough to walk through barefoot. Clean space equals clear thinking. It's not a rule I personally live by if you ever looked at my office, but it's a great rule. Number 7, skill posters. One-page visual standard operating procedures on the wall. New team members walk in and they get up to speed fast. Every practice eliminates a specific type of friction. Put them all together and the team just moves faster. Maybe I should clean my office. I want to walk you through a core engineering insight of XM. And the computer metaphor we talked about earlier makes it crystal clear. Old school lean manufacturing works like a single-threaded computer processor. Work flows in one direction, through one line, one station at a time. If station 3 breaks down, everything downstream stops. Dead. Zero output. The whole line is held hostage by the slowest bottleneck. Now, XM works like a multi-core processor. Instead of one long line, you have multiple independent cells. Lean cell A, B, C, D, E, F, etc., all running at the same time. They share a central stock back plane, basically a common inventory pool, and work is routed dynamically. And here's the beautiful part. If lean cell C hits a problem, say a machine goes down, work gets rerouted automatically to the other cells. Output drops, from 100% to 83%, not to zero. The factory stays active while the problem gets fixed. Think about what that means for a company. In traditional manufacturing, one machine failure can shut down thousands of workers. In XM, it's a local problem with a local fix. The global factory keeps running. This isn't just about efficiency, it's about resilience. The whole system is designed so that no single failure can stop everything. So let's come back to that claim I made earlier about making 27 hardware changes a week on a live production line without shutting it down. How do you do that? Well, you use the same techniques software developers use when they want to test a new feature without breaking the main product. You fork. That's a fork. And here's how it works. The main production line, the main branch, keeps running. Cars are flowing down the line, business as usual. At any point, a software router physically diverts exactly one car off of a pilot line, a smaller, separate lean cell. A cross-functional team experiments on that single car. They test the new component, the new process, the new design, whatever. When they're done, they check it against the definition of done, and that's the pass-fail criteria established in advance through that testing upfront phase, test plan up front. If it passes, that single car merges back into the main line, the change gets absorbed, volume production continues without interruption. Now, that's what Elon Musk called production hell, but Joe Justice reframes it. Production hell isn't a problem, it's just what it looks like when you're continuously running pilot lines alongside volume production. It looks chaotic on the outside. On the inside, it's a systematic innovation engine. It's a continuous improvement process. You never stop producing, you never stop improving, and things happen at the same time. So here's a question. If you make 27 hardware changes per week, how do you keep track of which version of the car is sitting in which customer's garage? Well, the old answer, paper batches, a stack of forms saying this batch has configuration X, slow, error prone, and really useless for real-time feedback. XM's answer, the digital twin. Every single unit that comes off the production line has its own unique digital record, a virtual replica stored in a database. The record knows every bolt, every firmware version, every stress test result. It knows that this specific car, unit 8849B, has the new front suspension module, firmware version 3.2, and passed the test on Tuesday. On the right side of this diagram, you can see what that digital twin looks like. It's not just a model, it's a live database linked to the physical unit. And here's where it gets powerful. The car literally tests itself. In factory mode, the car drives itself through a robotic testing track, water penetration tests, noise and vibration tests, alignment check, and the results feed back into the digital twin in real time. If something fails, you know immediately. You know which unit, which configuration, which change introduced the problem. This is how you maintain quality while moving at the speed of fast. You don't slow down. You make the testing automatic and continuous. Let's look at another big factor in XM. One of the biggest speed killers in a traditional manufacturing isn't in the factory itself, it's the supply chain. Traditional procurement goes like this. You design the part in full detail, exact specifications, dimensions, exact materials, tolerances, etc. You send a complete CAD file to live suppliers. They each spend months building a custom bid. You pick one. They spend more months building custom tooling. 18 months later, you get the part. 18 months for one part. XM flips this completely with one insight. Stop sending suppliers the solution. Send them the problem. You send two things. You send the interface spec. That's the contract that has to be between modules, what the part has to connect to, what force it has to handle, what the dimensions of the connection are. And then the test fixture, the automated test the part has to pass. That's it. You don't tell the supplier how to build it. You tell them what it has to do. And here's what happens. The case study on this slide is a real example. A team needed a transmission for a prototype tractor. Instead of an 18-month custom contract, they sent the interface constraints, dimensions, torque limits, etc., and the test fixture. The supplier matched it with off-the-shelf volume parts they already had in stock. Delivery, next day. Same need, 18 months versus next day. Now, when you shift from here's how to build it to here's what it has to do, you unlock your supplier's creativity and your own speed at the same time. Let's talk about what leadership looks like in an XM company, because it is completely different from what most of us have been taught to expect. Look at the left side of this diagram. Legacy leadership. The executives are in a conference room. There are presentations. There are approval chains. Someone on the factory floor has a problem, and it takes 2 weeks of meetings before a decision gets made. Well, Joe Justice calls this permission bottlenecks, and they're everywhere in traditional companies. Every decision that requires approval from someone not standing next to the machine, next to the problem, that's a bottleneck. Now look at the right side. XM leadership. The executives are on the factory floor. There are no presentations. When a bottleneck shows up, say a machine is down or a supplier is late, the leader is already there. They make the call in 60 seconds. XM calls this swarming the critical path. The most important thing a leader can do in this model is identify whatever is blocking the team right now and go remove it. Remove it. immediately in person. There's a principle called the law of 2 feet. You should always be standing where you add the highest value. In XM, that usually means on the floor, not in a conference room. And there's one more rule. There are no presentations. None. If you need a presentation to explain what's happening, you're already too far from the work. Walk out, look at the board, talk to the team, fix it. By now, you've seen a lot of ideas borrowed from software applied to physical hardware. And this slide makes that connection explicit and shows you exactly how the translation works. Every major concept in modern software engineering, object-oriented coded, has a hardware equivalent in XM. In software, an API or an application programming interface, that's the defined contract between two systems, how they talk to each other. In hardware, that's the physical interface contract. Same idea. Here's how we talk to each other. In software, a microservice is an independent piece of functionality that can be updated without touching the rest of the system. In hardware, that's a swappable module, an independent subassembly with defined interfaces on all sides. In software, a unit test is automated code that verifies a function works correctly. In hardware, that's factory mode, robotic automated testing of each physical unit. In software, when you want to try something without breaking the main code base, you branch out and commit. In hardware, that's the router fork, physically routing a single unit off a pilot line to test a change. The constraints that made hardware development slow, the multi-year cycles, the big batches, the siloed departments, those weren't physics, those were choices. They were a consequence of organizing hardware teams differently than software teams. But once you apply the same patterns, you get the same results. Hardware can move at the speed of software. I'm going to wrap this up by referring back to when we started. We asked, how long does it take to build a car? Let me end this by answering with 3 different ways. Wikispeed, a small volunteer team of about a dozen people, using extreme manufacturing principles, they designed, built, and tested a road-legal car that gets 100 miles per gallon and passes European crash test safety standards in 27 minutes per prototype iteration. A car, 27 minutes between prototype iterations. Saab Gripen, that's a fighter jet, and it's one of the most complex machines humans build. And using XM-inspired 3-week sprints, they're approving hardware and software updates that used to require years of certification cycles. SpaceX, their Raptor engine, the most powerful rocket engine ever built, fully designed, built, and test-fired in 2 days. 2 days for a rocket engine. This slide shows the edge of chaos, a concept from complexity science. Most organizations live in one or two places. Either they're in the obvious or the complicated zone, predictable but slow, or they fall off the failure cliff into pure chaos, fast but destructive. XM operates exactly at the edge between these two. Enough structure to be safe, enough freedom to be fast. That balance is what you're aiming for. So here's the takeaway from everything we've covered. The constraints that make hardware development slow are not physical, they are organizational. Change how you structure your team, your interfaces, your testing, and your leadership. And physical products can move at the speed of thought. The floor is open. Let's build something. Thank you again for paying attention to these presentations. I greatly appreciate it.